Okay, everybody, today I'm going to do a lecture on equilibrium, and then I will do another one also for your thorough use. The one today should be enough so you can understand this week's lab. So basically what I want to do first is introduce it to you, and then we'll talk about the rest of it. But right now I'm going to get everything set up and stop my video, but hopefully you can still hear me. What I'm going to do now is open up the spreadsheet for you and talk about the nature of the reactions and how they work. So let's get going with this. Okay, so now I'm going to share the screen with you folks, and then we'll continue. Okay, now this is essentially the nature of the chapter. This is an intro to chemistry textbook. So we'll cover it, and then I'll use our textbook to kind of finish off the chapter. But I want to introduce it to you better this way. This will hopefully help you understand it a little better. And the main things about this, you start off with the reversible reactions here, rates of reaction, chemical equilibrium, Le Chatelier's principle, the effect of concentration and equilibrium, effect of volume, temperature, catalysts, etc. And then the ion constant, acid-base properties of salts, and then buffer solutions to talk about the control of pH. So it'll introduce you to both this chapter, which is equilibrium in your textbook, as well as the next one, which is on acids and bases. So it's kind of an introductory to both of the things we're going to essentially do. So now what I'm going to do is get the pointer ready, and then we'll go through the slides. The key thing to understand about the nature of reactions is many of them are reversible. And if you start off with a very simple one like this, sodium hydroxide plus carbon dioxide leading to sodium hydrogen carbonate. This will go in both directions depending on what the conditions are. If you have sodium hydroxide in the presence of carbon dioxide gas, it will form sodium bicarb. But if you heat this on this side, it will go the other way. So there's an equilibrium aspect to this. And so basically your energy diagram will kind of look like this, where it'd be kind of low, higher like that. And if you have an exothermic reaction of sodium hydroxide and carbon dioxide reacting together to form this, it'll go in this direction, but it'll also go back in the other direction. So you can get both of the things occurring at the same time. And the key thing is reversing the reaction going, and it's kind of like if you have a ball on a very low hill, you could push it over one side and then push it back the other fairly easily. And if there's another energy in the system, essentially it'll go back and forth, depending on that. A reversible reaction is a chemical reaction in which the products formed react to produce the original reactants. For example, the reaction between NO2 and N2O4 is reversible. When you cool nitrogen dioxide, it'll form dinitrogen tetroxide. And essentially, if you heat it, it'll go the other direction. So the heat in this case is enough. So essentially, cooling this would mean you have heat coming out the other side, you're removing heat from the system, and then heating on this side, you add heat on that side, and it'll go over to the other side. So basically, this is an example of a reversible reaction. And if under certain conditions, if you got the energy diagram, it looks like this, where it's relatively small between, and you've got enough heat in the system, it'll go back and forth and back and forth, going back and forth across that hump fairly easily in both directions. So let me erase what's on the slide, and then you can see a little better regarding how that works there. Okay, so basically the way it's represented is with these double arrows. You have those going in two directions like that. The reaction to the right there, and then the reaction to the left going the other way. And then here's going back and forth regarding that. The rates of reaction are important to understand. And essentially, we were talking about that in the previous chapter, the study of the reaction rates and reaction mechanisms. The rate of reaction is variable. It depends on the concentration of the reacting species, the reaction temperature, the presence or absence of catalysts, which essentially changes the reaction path, and then the nature of the reactants together. And if you have the rate of the forward reaction here, and then the rate of the reverse becomes the same, you have what's called an equilibrium condition, where the rate forward is equal to the rate going back. And so that's when you have an equilibrium system that looks like this, where you've got a system there, and it goes back and forth and back and forth, and there's always parts on the A, B, and C there, and so A, B, and C are always present. Always present. And if you remember when we talked about it in the kinetics thing here, when you have this thing with an activated system, this is A plus B, and this is a combination of A and B kind of together. So for example, let me use another example here. Where you have H and chlorine reacting with each other. Okay, you have H2 plus chlorine under certain conditions, and you start at that point, and it goes up like that and then down the other way. And so essentially what you're trying to get is 2HCl down here, and then you have H2 plus Cl2 here on that side. Here you might have an intermediate form that'll look like this, and the chlorine like this, with bonds forming there and bonds breaking. So these form while those break, and then you end up going back in that direction or that direction. And if the conditions are right, it could go back and forth through this, what is called intermediate. And so let me erase what's on the slide again. You can see how this kind of works here again. The concentration of A and B decreases with time, lowering the rate of the forward reaction. The reverse reaction is going the other way. So you have this going back the other way there, or this going forward. And so you got the rate going back and forth under equilibrium conditions. That's when the rates are equal. Now, chemical equilibrium is a dynamic state in two or more opposing processes are taking place at the same time and at the same rate. Chemical equilibrium is the state in which the rate of the forward reaction equals the rate of the reverse reaction in a chemical change. At equilibrium, the concentration of the products and the reactants are not changing. They're continuing to go back and forth across this little hump. And essentially you got the rate forward equals the rate reverse. And so essentially you've got both of them together. And so you have always stuff at the A point, you have stuff at the B point, you have stuff at the C point, and it never changes because it's constantly going back and forth across that hump. Now let's look at a saturated salt solution. And here you have sodium chloride in solution here with water. You have under the conditions of reacting it with water. And basically, essentially, some will be dissolve at the same time, and recrystallize. At the same time. Very important. Salt crystals are dissolving, and the sodium and the chlorine are recrystallizing. At the equilibrium, the rate of salt dissolution equals the rate of salt crystallization. Now, Le Chatelier's principle is very important, and I've done at other schools labs that kind of illustrate this thing. And this is a very, very important aspect of equilibrium. And in 1988, the French chemist Henri Le Chatelier set forth the far-reaching generalization of the behavior of equilibrium systems. This generalization, known as Le Chatelier's principle, if a stress or strain is applied to a system in equilibrium, the system will respond in such a way to relieve that stress and restore equilibrium under a new set of conditions. So the effect of concentration in equilibrium is important. For most reactions, the rate of reaction increases as the reactant concentrations increase. So basically, if you have A plus B goes to C, if you add A, more will react. Okay? So basically you have more go to the right there if you add A, or if you add more B, more will react. The manner in which the rate of concentration changes to the constant must be determined experimentally. An equilibrium is disturbed when the concentration of one or more of its components is changed. As a result, the concentration of all the species will change and a new equilibrium mixture will be established. And that's what you did 2 weeks ago when you set up the two solutions. And essentially you started the reaction by adding hydrochloric acid to both of them, and then see what would happen under those reaction conditions. And over the 2 week or 3 week time frame, you ended up getting equilibrium established where we go back and forth across the hump. And essentially, again, the best way to remember it is like this, and when the hump is relatively low, and you got to go back and forth, and essentially the concentration stable across the whole everything. So they stay the same even though individual molecules and atoms are getting transformed one way or the other. This system is at equilibrium. So what do you think is going to happen if you increase the concentration of B? Think about it a little bit. Well, it'll drive it to the right. It results in A and B being used faster than they are produced. And the reason is you get more collisions. Okay? And more orientations to enable those reactions to take place. Get C and D produced faster than they are used. It increases the rate of the forward reaction. Okay? After enough time has passed, the rates of the forward and reverse reactions become equal. So you've now reached a new equilibrium, The system's again at equilibrium. The concentration of A is decreased. The concentration of B, C, and D have increased. And after enough time has passed, essentially you get that. Now, percent yield is sometimes affected when this occurs. For example, at 700 degrees Kelvin, if you have the reaction of hydrogen gas with iodine gas, you'll get HCl, hydrogen iodide in water at 700 K. H2 and I2 combine to form HI. HI decomposes to form their H2 plus I2, and essentially, I don't know why they have AQ there. What I'm going to do now is kind of go back on this a little bit. And I'm going to change the screen and fix this. At 700 degrees, HI is a gas also. So it's important to keep that in mind here. So let me go back to the slides now and help you with understand that. I've shared the screen again here. Okay, you've got the H2 going to HI gas there at 700 degrees Kelvin. Okay, HI decomposes things. And again, at 700 K, you've got a reaction like this, where you have this on this side. You have the H2 plus I2 over here. You have the 2HI over here. And in the intermediate, you have the intermediate form here, where these bonds are forming and these bonds are breaking. And so basically it'll go back and forth across that. Okay, so we start off with 1 mole of each of them, and 2 moles of the HI. The final concentrations in the absence of equilibrium. So if you did not have an equilibrium, like if it looked like this, so essentially it all goes all the way down there. This going back is too high to reverse. Okay, so basically we won't go that, but notice this is at 700 degrees Kelvin, which is about 400 Celsius. Okay, so essentially at that temperature, it essentially enables them to have enough energy to go back the other direction. So essentially at equilibrium, it'll go back the other way. The forward reaction is 79% complete at equilibrium. So at 700 K, this will have some that go back that direction. Some will go back there, but it's 79% complete over here. The yield will be 1.58 moles of HI divided by 2 is 79% reaction there. You start off with initial if you change the initial concentrations to both, you increase iodine gas there. The final equilibriums will, in the absence of equilibrium, you get 2 moles of HI. And notice this is extra. Okay. But at equilibrium concentration, you get 0.15, 0.35 there, and essentially you have 1.7 moles, and so the yield ends up being a little higher. So essentially you've added iodine to the left and forced you to get more product on the right. Now, if we look at comparisons of equilibrium there, here, if you essentially you have started with 1 mole of this and 1 mole of that, you get 79% HI, and this is 1 mole of this and 1.2. You've added to this, you get 85%, and so now the equilibrium mixture looks like this, and so essentially this is higher than it would be otherwise. Now, the effects of concentration changes on the chlorine-water equilibrium. So if we look at dissolving chlorine in water, it'll react to form hypochlorous acid there. If you decrease this concentration, you remove it from this side, remove, what's going to happen? Well, it'll drag it to the left. If you decrease that concentration, it'll shift to the left. That's what Lachey's principle says. Like the previous one where you have HI, H2 plus I2 going to 2HI, you added I2, and that drove it to the right. Okay, here you remove the chlorine, decrease the concentration there of chlorine because it would be as a gas. So if you heat it up a little bit, that'll remove the chlorine gas, and so that'll cause it to go to the left. If you increase the water concentration, it'll shift to the right because more of the chlorine will dissolve, will react with the water there if you increase the amount of water in the system. If you increase the amount of hypochlorous acid, it'll go to the left. There, if you decrease the acid concentration, it'll shift to the right. And if you increase chlorine, it'll shift to the left. So that's Le Chatelier's principle there. So now let's look at the next one. The effect for this is acetic acid, and this is the lab that we're going to be doing next week. Concentration changes on pH. So essentially you start off with 1 molar, and the pH at equilibrium is 2.87, and this is called a weak acid because of that. 2.87 is a weak acid, whereas if the pH was equal to 1, that would be a strong acid. Okay. And if you add sodium acetate to it, you're essentially adding this ion here to it, to that side. It will drive it to the left that way. Okay, because you have this extra ion here and you're putting more in on that side, it will drive it to the left. So the equilibrium shifts to the left there, and the new pH will be 4.74. You add extra there, it goes 1, then 2, it goes higher to 5.05. Now the effect of volume in equilibrium, changes in volume significantly affect the reaction rate only when one or more of the reactants is a gas and the reaction is run in the closed container, because you have more collisions, and more in right orientation. The effect of decrease in the volume is to increase the concentration of any reacts also. So essentially, if you increase the volume, the decrease in the volume increase the concentrations there. So giving more collisions and more in a certain direction there. So if we look at an example here of calcium carbonate as a solid with a gas on the right, if you decrease the volume, what will that do? That will increase the pressure. So basically that'll increase the pressure of this. So more will want to react with this. And so essentially you get calcium carbonate over there. It increases the concentration in a certain volume, then they'll shift it to the left. If you increase the volume, like put a vacuum on it, or remove the CO2, or if you remove the CO2, you'll essentially do this, essentially go in that direction. The equilibrium will shift to the right. If a system composed of entirely of gases, a decrease in the volume of the container will cause a reaction and the equilibrium to shift to the side that contains the smallest number of molecules. So let's look at an example here of nitrogen plus hydrogen forming ammonia. There, you have a certain number of molecules on the left and the right. If you have 1 mole of nitrogen to 3 moles on that side and 2 moles in the middle, this will have 4 moles on this side, and this will be 2 moles on that side. It's essentially, if you decrease the volume, it'll shift to the right towards fewer molecules. Okay, or if you have this system where you have 1 mole plus 2, that essentially you have 2 moles on one side and 2 on the other, that is equal. So that change in the volume will have no effect there. But if you decrease the volume, essentially there, that'll increase the pressure. So essentially you get an increase in pressure. More collisions. The equilibrium does not shift. The number of molecules is the same on both sides because they'll go back and forth, and essentially increasing the pressure will be the whole thing. So there's no change here. This is 2 moles to 2 moles to 2, so no change. If you decrease the volume or increase the volume, they're there. Effective temperature at equilibrium, that depends on the conditions. When the temperature of a system is raised, the rate of the reaction increases. And again, if you look at an energy diagram, if you look like this and you increase the energy, essentially you have this activation energy. So more will go in this direction, but more will also go back the other way if you have enough energy in the system that the rate of reaction will, going forward, will increase, as well as the rate of reaction going backwards also increase. So both of them increase. In a reversible reaction, the rates of both the forward and the reverse are increased by an increase in temperature. The rate of reaction that absorbs heat is increased to a greater extent, and the equilibrium shifts to favor that reaction. So if you've got heat plus, for example, sodium hydrogen carbonate will go to form sodium hydroxide and carbon dioxide. So if you put heat on this side, that will drive it to the right. But if you cool it down and remove heat from it, it will cause it to go the other way. Or if you add CO2 to that, add CO2, it'll force it to go to the left. So basically you got those things shifting. At room temperature, very little carbon monoxide forms when you have the combination of both in the presence of heat. But at 1,000 degrees Celsius, the moles of the carbon dioxide will approximately equal the moles of the carbon monoxide. The equilibrium will shift to the right because essentially what you've done is you added heat to this system. So essentially adding heat there will force it to go to the right. But because essentially you're changing the reaction conditions and enabling the activation energy to change. The effect of catalysts on equilibrium. A catalyst is a substance that influences the rate of reaction and can be recovered essentially unchanged at the end of the reaction. It does not shift the equilibrium. It only affects the speed at which the equilibrium is raised. And if you look at the reaction that we showed, so for example, if you got a reaction like this with no catalyst, and then you add a catalyst that forces it to go like that. This has a catalyst. It'll go better to the right, but it'll also go better to the left. So basically it'll go back. The catalyst will enable it to go faster to the right and the left. To go to the right and to the left. Changing it. So essentially you've got a curve that looks like this, like that, and then you got another one that looks like this. Then you got another one that looks like this with another pathway. And so essentially this is the same reaction, but now you can go back and forth better under those conditions. So essentially the catalyst has changed the reaction conditions, and so you will get a faster reach equilibrium. So if you look at these things with the catalyst, you have a certain energy, activation energy here, and then adding the catalyst to it. Now this will go back and forth across there easier because you got energy, the reactants more will be able to go back the other direction. The activation energy is the minimum energy required for a reaction to occur. A catalyst speeds up the reaction by lowering the activation energy. It does not change the energy of the reaction. For example, if you have this reaction to form thiophosphoryl chloride, because the reaction is so slow, but a catalyst, you got the reaction is complete in a few seconds. So this might be a diagram that looks like this, where you've got a very high activation energy that goes there, and then you switch it to form the other one, and now you start at this point again, and you get a lower one. So basically, this is enough to enable that to go to completion, whereas this is too high without the catalyst over here. The laboratory preparation of oxygen uses manganese dioxide, in this case, to do this, and that's one of the labs that we did a couple weeks ago. Manganese dioxide is a catalyst to increase the rate of reaction. Okay, now equilibrium constants, the next thing, this is what we're going to be calculating for this week's lab. At equilibrium, the rates of the forward and the reverse reactions are equal. The concentrations are constant. The equilibrium constant is a value representing the unchanging concentrations of the reactants and the products at equilibrium. So for a general reaction at a given temperature, the equilibrium constant is equal to this. And notice it is the products over the reactants. And essentially you can measure the different values when you do a certain experiment there. So if you got a reaction between hydrogen and nitrogen to form ammonia, the equilibrium concentration is there. And then you have the other one for there with this, equal that. The magnitude of the equilibrium constant indicates the extent to which the forward and reverse reactions take place. So here, if you have 3 hydrogens plus iodine going to that, you're essentially adding H2 to go to 3, so you force it to go in that direction. So essentially, this is a high number, so that'll say it will go to the right. At equilibrium, more product than reactant exists, okay? And in this case, with thionyl chloride, there at 400 degrees Celsius, it's very low. And so basically, when you have the concentrations of that is very, very low, this means at 400 degrees Celsius, it's almost always in that form to the left under those conditions at 400 things, because basically what you're doing is providing enough energy for this to react with that, to have it go back in that direction. So essentially you have much more on the left than you do on the right. And that's why that's a very low number, because you're dividing by a big number. This is small and this is very big. So that's a very low number there. The equilibrium, more reactant than products exist there. When the molar concentrations of all the species in equilibrium reaction are known, the KEQ can be calculated by substituting the concentrations into the equilibrium expression. Now calculate the KEQ for the following reaction on PCl5, where you have PCl equals 0.3 moles per liter. The PCl3 is 0.97 and chlorine is 0.97 at 300 degrees Celsius. Well, you set it up that way. So you got the KEQ is 31. So that's 31. This is a high number. So that tells you it'll go to the right. So basically the reaction will have much more products on the right there with that high number. Ion product constants for water. Water ionizes to a slight degree there. And essentially more simple, you have dissociation there between them at equilibrium. This is the hydrogen ion concentration equals hydroxide ion concentration. This is 1 times 10 to the minus 7. So you have the pH is equal to the negative log of the hydrogen ion concentration, which is a negative log of 1 times 10 to the minus 7. That's where you have a pH of 7 under that condition. So that is called neutral under those conditions. And this gets into the definitions of acids and bases when we get to that next chapter. The water equilibrium constant is called the ion product constant for water. So at 25 degrees C, it's 1 times 10 to the minus 14. What is the concentration of H plus and OH minus in a 0.1 molar HCl solution? HCl is 100% ionized. So essentially the H plus is 1 times 10 to the minus 3. Solve it for OH. Well, you plug the numbers in and you can get the different values each there. And then you get 1 times 10 to the minus 11 moles is the moles per liter is the concentration of OH. And under those conditions, you can determine the pH there. So what is a pH of a 0.01 molar sodium hydroxide solution? Sodium hydroxide is ionized. The OH concentration is 1 times 10 to the minus 2. You solve it for H plus. You have that's 1 times 10 to the minus 14. You plug the values in there. And then you get the pH is equal to the negative log of this number, 1 times 10 to the minus 12. And essentially that will then equal 12. The pH may be calculated also by calculating pOH there first if you wish to do that. Okay, so in pure water, pH plus pOH is 14. Then you can calculate it that way. So if you look at different concentrations related to each of them, essentially these are acids there, and these are bases, and the bases here. So essentially for this one is a base. This is neutral. Ionization constants, and in addition to Kw, several other ionization constants are used. Ka, acetic acid ionizes water, the following equilibrium is established. And again, with this is a weak acid. So in water, you have this present. And this is what you can smell. You couldn't smell it if there wasn't as a molecule. You can smell it as a molecule. Whereas these are no fragrance. These are no fragrance for them. Okay, so you can smell the molecule on that side. So that kind of is proof of the fact that you have an equilibrium there. The ionization constant for this equilibrium there, Ka equals H plus times the concentration there. Well, the acid ionization constant, since the concentration of water is large, it doesn't change, it's omitted from Ka. So a 0.1 molar solution is 1.34% ionized, and is H concentration 1.34 times 10 to the minus 3. Calculate the Ki for it, Ka. So basically you can then solve for Ka this way, and you can look at these different slides yourself. What is our H plus concentration in a 0.5 molar acetic acid solution? The ionization constant Ka for that is 1.8 times 10 to the minus 5. You plug those values in there. The concentration of the two ions are equal here. Each molecule gives one of these and one of that. So essentially you've got the H plus is equal to that one. So let Y equal the H plus. So that is 0.5 minus Y. You substitute the values in for each value there. You have Y squared and 0.5 minus Y. 1.8 times 10 to the minus 5 is your answer. And I'd recommend you read that part in the book and take the square root of both sides to get that final answer. So basically using a quadratic equation, you'll get a similar number there. Calculate the percent ionization of a 0.5 molar acetic acid solution. The ionization of a weak acid is there. Ionization constants of weak acids at 25 degrees Celsius there. And then the last part is solubility thing. You have a dynamic state in which two or more opposing processes are taking place at the same time. KSP is with a slightly soluble salt. Silver chloride, this is mostly solid. It doesn't dissolve in water, just like if you did the reaction sodium chloride plus silver nitrate, like we did last semester, you get silver chloride plus sodium nitrate in solution, AQ, but basically it'll go back the other way too there. There's an equilibrium associated with that. And the amount of the solid is a constant, so you can rearrange that. And so the KSP is equal to the silver ion times the chlorine. And that's essentially that. The solubility of silver chloride is 1.3 times 10 to the minus 5, because each of the formula unit that dissolves, the concentrations are equal for both. And then the KSP has no denominator under those conditions, and that's the KSP. When the product of the molar concentrations of ions in a solution is greater than KSP for that substance, precipitation will occur. The KSP value for lead sulfate, calculate the solubility of that in grams per liter. And again, you've got the different interactions there between both. And then you can figure out what the values are using that process. And I think that's where I will stop today for this portion of the lecture, and continue this later in the other text, in the main textbook. But I think I've introduced the whole concept of equilibrium so you can get that fairly clearly. Okay, so basically I've introduced you to the subject of equilibrium. I'll continue the rest of it in my next lecture. I'll probably do that tomorrow afternoon. Then you'll have enough for things, but based on what I did today, that'll help you understand what you're doing for the lab next week. So thank you all for your attention.